What is it about Rootstock, Bitcoin, and blockchains in general that you find interesting? What is it that gets you out of bed in the morning and wants to work in this space?
Well, I actually knew about Rootstock while I was at IBM because we shared some conferences. At the time, I was a more permission blockchain guy because that's what I was working on. So I didn't really know much about the public blockchain space, the permissionless blockchains that anyone can participate. That's really what drove me to this space, the fact that these are for everyone. It tries to democratize the access to these technologies. The ultimate goal, which is enabling everyone to participate in whatever protocol we build on top of our blockchain, for example, decentralized finance or everyday DeFi, etc.
Welcome to Rootstock Fundamentals, a series of conversations with some of the key contributors to Rootstock, Bitcoin's first and longest running sidechain. We've designed this series as a beginner's guide to Rootstock. We're exploring Rootstock's origins, its cryptographic connection to Bitcoin, the security model used to protect Rootstock, and how the Rootstock network continues to evolve today. Rootstock was the first Bitcoin sidechain. It brings together the benefits of Bitcoin, security, store of value, widespread adoption and decentralization, with the benefits of Ethereum, smart contracts, programmability, token utility, and an active developer community. This combination makes Rootstock the most secure smart contract platform on the planet. And this episode, I'm joined by Raul Laprida, Director of Architecture at RootstockLabs and long-term contributor to Rootstock. We're going to talk merge mining, proof of work consensus mechanisms, and talk in general about Rootstock's cryptographic and economic connection to Bitcoin. So, hey Raul, welcome to Rootstock Fundamentals.
Thank you. Thank you for having me, Daniel.
It's nice to have you out here on the video on the internet. So Raul, let me ask the classic first question on any interview related to Bitcoin. When did you first buy Bitcoin? Or when did you first receive Bitcoin?
No, the first time I bought Bitcoin, well, we know I'm from Argentina, pretty unstable country in terms of purchasing power. So at that time, I was working at IBM and I was starting working with blockchains, different type of blockchain, but regardless, then I was interested in Bitcoin, and it was when I purchased my first share of Bitcoin. It wasn't a Bitcoin, but it was a part of a Bitcoin.
And you joined RootstockLabs after IBM in late 2018.
Yes.
And I know you've worked on many of Rootstock's breakthrough innovations and also some of the Rift protocols as well. Can you maybe give me a brief run through of your contributions to Rootstock over the last 5 or 6 years?
Yeah, it's been almost 5 or 6 years. So when I started, it was, I don't know, it was RSK Smart, I think. I don't remember the name. Smart Labs. And I started as a researcher. The first things that I had to do was actually writing the Rift white papers. And I was involved in a bunch of them. The Rift, the Oracle's one, at that time it was called Data Services. Then it morphed to a different name, Rift Communications, part of Rift Storage. Then I created a performance tool for the node that's actually being used right now. It was used to to run synthetic runs of blockchains that you can actually auto-generate with a tool that I created, and then you can perform these sort of metrics and get some insights of the node. I'm probably going to forget a lot of things, but then I created, we had an attempt at the creation of permission blockchain. Given my background at IBM, I worked with permission blockchains back then, to create a permission version of our node of our blockchain using Besu, Hyperledger Besu. Then I worked with Reef Relay, which is basically what it allows. It allows a user to pay for their transactions using any other ERC20 token instead of the native cryptocurrency, which is RBTC. And
so
that's
getting around the need for having RBTC in your wallet in order to transact.
Right, exactly. And it uses this concept of smart wallet. Actually, the smart wallet that we created is very innovative. We did it entirely in machine code, EVM code. So it's very performant and it's very small. And yeah, after that, well, I changed roles, right? And I became the head of architecture. And I started overseeing making sure that the soundness of all the components that we create and maintain is good, right? And well, now I transition to director of architecture. Basically, it's the same responsibilities.
And so it's been quite a journey. How much of your own code is in the main Rootstock blockchain, and how much of it is in some of the connected Rift protocols?
Well, yes. Well, not taking into consideration the written words from all the white papers, in terms of code, we created a proof of concept for the Rift communication one, which is the things that we did. It was a decentralized peer-to-peer connection layer, which had it was encrypted. Actually, has forward secrecy, and it used something called forward cademia. At that point, it wasn't an implementation done yet, so we had to create it. From there, I would say, yeah, I don't know, 80% was my code. Then for the Rootstock node, I don't know, but it's nothing compared to what other people had contributed, so I wouldn't have like an estimate. It's massive. Then for Rift Relay, I could say 98% of the initial release is my code. So yeah, it was a very hard work, but yeah.
And maybe this gets to the heart of something which is not just true for Rootstock, but any open source project, which is that there are hundreds of people that have contributed to Rootstock over the many years. And it really has been a wide community effort in building out what we know as Rootstock today. And maybe on a personal level, what is it about Rootstock, Bitcoin, and blockchains in general that you find interesting? What is it that gets you out of bed in the morning and wants to work in this space?
Well, I actually knew about Rootstock while I was at IBM because we shared some conferences. At the time, I was a more permission blockchain guy because that's what I was working on. So I didn't really know much about the public blockchain space, the permissionless blockchains that anyone can participate. That's really what drove me to this space, the fact that these are for everyone. Yeah, it tries to democratize the access to these technologies. The ultimate goal, which is enabling everyone to participate in whatever protocol we build on top of our blockchain. For example, decentralized finance or everyday DeFi, etc.
So it's the kind of open, permissionless quality. It's infrastructure for everyone, not just infrastructure for a particular company, a particular sector, a particular type of person. It's an open protocol network.
Yeah, and particularly Rootstock being a sidechain of Bitcoin is enhancing, the capabilities of Bitcoin, so it's even more attractive as one of the options as one of the public blockchains available is, for me, one of the most attractive options because of that.
All right, great. Well, that moves us really nicely into the first question, really. So what is proof of work? And are there any other consensus mechanisms other than proof of work? We're going to start at the very top, and then we're going to work our way down into Rootstock specifically.
Okay. Well, yes. First of all, I would remark the problem that we're trying to solve, right? Which is right now we live in, or we are interacting with this digital world, which is mostly centralized, right? We're trying to come up with this solution, which is being able to agree on a single version of the truth, whatever that is, and without relying on a central authority. For blockchain specifically, that's the public ledger that we all know. What mining is interchangeably with proof of work. They can be used as synonyms. Is the engine that powers this decentralized consensus that we're trying to build. It's democratic and it's secure, a secure method for agreeing on the stage of this single truth, or for the blockchain, the ledger. What we are doing is shifting our trust. Initially, what's on institutions or centralized authority, we're shifting it to the other side of the spectrum. In this case, is the laws of mathematics, for now unbreakable, and cryptography. We say this is democratic because anyone can participate in these public blockchains, and anyone can build and propose the new state of the truth, which is the blocks. The way they do it is they just create it, but they need to put a significant amount of work in order to submit it to the network and in order to be accepted by the rest of the participants. And that's the proof of work, is solving a computationally difficult cryptographic puzzle, whatever that is. We are not going to explain right now what that is, but it is what you need to do. And in order to do it, you are going to spend resources in the form of electricity to power your computation, your computational power for your machines. The other question, if there are other, yes, there are many other. The most popular probably one is the one that Ethereum uses now, proof of stake. It's completely different. Instead of having miners competing, you have validators who are chosen in a streamlined way to propose a new block. And the way it works is they put a stake in something that is valuable, money, as a collateral. The selection is probably proportional to the amount of stake that they're putting. There are other ones, for example, delegated proof of stake. It's an improvement in terms of scalability of proof of stake. Then you have PBFT, which is the one I knew the most before coming to Rootstock. It's the one that is used in most of the permission blockchains. BFT is a condition that is used in distributed systems such as the ones that we're discussing here. It tells you that the system can remain fault tolerant, meaning that it works in a simplified, trying to be simple here, as long as the amount of malicious actors are under a certain bounded number. That's what BFT means. Then you have the whole suite or immediate of proof of X algorithms. Basically, the X is the scarce resource that you are putting. It could be proof of authority, which is similar to PBFT, but it's more performant. It has less rounds in the protocol. Proof of activity. And I think these are self-explanatory, right? Proof of importance, proof of elapsed time. So you are proving that a certain amount of time has passed, proof of reputation, etc.
Okay, so different ways to prove or different ways to achieve consensus. Proof of work being the one that Bitcoin uses, proof of stake being the one that Ethereum now uses, and many other Ethereum virtual machines, but not all. And then a long tail. Are there any within that long tail that are particularly novel or particularly interesting that you think are noteworthy and worth talking about here?
Not really. Well, maybe proof of elapsed time. For me,
proof of elapsed time.
For me, it's interesting. It's if you manage to do it not computationally intensive, is another way of proving that a time has passed, which is basically what you do when you're trying to solve the cryptographic puzzle, right? Because you don't care about the actual output of the puzzle. You're just worried about the resources that you're putting. But to be honest, I don't know of the details of a blockchain using that at the moment.
Okay, very cool. So Bitcoin specifically, so we've got an understanding of what proof of work is, and we've touched on this a little bit. So what is Bitcoin mining? Just at a brief level, and then maybe let's go into a bit of detail about hashing power more generally. What is Bitcoin mining?
Well, in a sentence, it will be the proof of work applied on Bitcoin, right? But going into much more detail.
Maybe let's start with this, just for people's benefit. What is a miner?
Well, a miner is a participant of the consensus protocol on a particular blockchain network that is going to propose the new blocks and create the work that's necessary to have that block accepted. That's the reason why it's called mine, because you need to do some work in order for your. I don't think it's the camera. Okay, it's working, the camera, right?
Yeah, we got you back.
Yes. So that's what a miner is. They are putting some work in order to have their block accepted. In Bitcoin specifically, we use a consensus mechanism called Nakamoto consensus. It's again a Byzantine fault-tolerant type of consensus. And it centers around proof of work, which is the mining part, or looking for this solution of the cryptographic puzzle, and a selection rule. So the way that the other nodes select which block is the next best block, assuming there are competing blocks.
And maybe so visually speaking, when we're talking about a miner, if you were to visualize one, we're talking about, they're often, they're referred to as ASIC rigs, right? So this is essentially a rack-mounted computer full of what used to be, I believe, GPUs, so gaming processing units, which could crunch massive amounts of data. So relatively simple computation, but able to be done at a very fast and large scale. And there would be hundreds of miners, right? So usually when you've got a mining pool, you would have hundreds of these ASIC rigs. So if you can visualize them, we're essentially looking at a sort of particular type of data center. That's essentially what a mining pool would look like if you were stood in front of one today, right?
Yeah, it's basically a bunch of machines brute forcing an input, trying to get a single output that it's the one that allows them to publish the block.
And you mentioned you used the word Byzantine.
Yes.
So we're talking here. Can you just explain a little bit around where that fits into the description you're using?
It's the general Byzantine problem. Basically, is how can you ensure that by giving an instruction to someone, that instruction is going to get an alter to the final destination. And basically, when you have an algorithm that is Byzantine fault tolerant, it ensures you that the message is going to arrive unaltered as long as the adversaries or the malicious actors within your network are below a certain threshold. So as long as you are below that certain threshold, you don't need to care about those malicious actors. The protocol ensures that the message is going to be correctly delivered.
Okay, so proof of work consensus mechanism being run by Bitcoin miners, which are these ASIC rigs, and the miners are trying to find an answer to a particular puzzle. And the first miner that finds the answer gets the reward, and that reward's in Bitcoin. When we talk about hashing power, then within this puzzle of the miners and the proof of work consensus and the problem they're trying to solve, what is hashing power and why is it so important?
Yeah, hashing power, first of all, is a unit of measure. It's the speed at which these miners can find solution candidates. So it's not the speed at which they can find the solution, but the candidates. So roughly speaking, the speed at which they can apply these hash functions to the input. And in Bitcoin, this is a double hash. So when you're talking about the hash rate, is the rate at which they can apply this double hash. So it's two hashes. If you want to understand why is it important, we need to understand how the cryptographic puzzle works. Trying not to be too technical, you have the function that you apply, which is the double hash, the input and an output. Your input is going to be the block that you want to mine, right? Which is fixed. And then you have a variable part, which is the one that you're going to play with in order to brute force the output that you want. And when you say that you need to find a valid or solve the puzzle, it means that the number that you get, the output, you need to compare it to something that the network is providing you, which is another number, which is called the target. Just think of it as a number. And in order to solve the puzzle, you need, as an output of your function, you need to find a number that is lower than the one that the network is asking you to solve. So if, for example, if the network has a target of 2, you need to find a number that is less than 2. And in order to do this, you have this variable part of your input that you increase. For example, if you think of it as a nonce, and you try to brute force it until you get a solution that is below this target. And for us humans to understand what this means, you can think of it as this way. This number has a minimum value that the network is going to set, and a maximum. So you have a range of potential values for this target that the network is giving you. And the lower the target, the smaller the potential subset of solutions you can have from this function. So the harder it's going to be for your machines to find a solution that is below the number. So the smaller the target, the harder is the difficulty of getting a solution for that block. And that's where the concept of difficulty comes into play. It is a measure of how hard, in terms of hashing power, it is going to be to find the current solution for the block that you're trying to mine. Yeah, sorry.
So when when people talk about hashing power, they refer to it in exahashes, and we are essentially talking here. Correct me if I'm wrong. We're essentially talking here about raw computing power that's being used to find a solution to the problem. So could this be envisaged as let's make the connection to Rootstock at a later point, because I think that this does start to explain how Rootstock merge mining works. But maybe let's move on now to merge mining.
Okay.
Well, in fact, let's do scale first. Do you know today how much hashing power is being used on the Bitcoin blockchain?
No,
I mean, obviously not looking for live data, but like roughly, do you have an understanding of how much is being used?
I don't have the number. It is a lot. It's I think it's in the terahash realm instead of exahash. But yeah, I don't. We can easily go and look for it. But in terms of hashing power, yes, it is measuring. It's basically hashes per second, and not just a hash, but the double hash.
Right.
That's important.
Okay, so Bitcoin blockchain using proof of work consensus, the miners trying to solve the puzzles, millions of miners trying to solve this simultaneously. What then is, and that's how Bitcoin achieves consensus and prevents, for example, forking of the cloning of the network, false blocks, and many other issues. What then is merge mining?
Well, the concept
maybe let's do a brief answer, and then we'll dive into exactly how it works. How would you describe it at a high level?
It's very simple. It's basically mining more than one blockchain for the price of one. That's the simplest answer. What it means
having
is
multiple blockchains being able to anchor into the cryptographic hash rate of one blockchain. So you're not requiring to run 8 or 10 different proof of work mechanisms necessarily. You're all anchoring into the same one.
Yeah. So basically what you do, you have your block, the primary blockchain block. Primary blockchain is the blockchain that you usually mine. In the case of Bitcoin miners, it's going to be Bitcoin. And then all the secondary blockchains are the ones that you want to merge mine. And what you do, you put a sort of reference of the secondary blockchain blocks in your block, the primary blockchain block, and then you create the proof of work solution as usual. So you're just doing one proof of work. But since you have the reference to those blocks in your block, that way you are solving the problem for all the merge mine blockchains, which can be more than one if you want.
So how, so you've started there, but maybe let's go into a bit more detail. So how does it work? How does merge mining work? And maybe at this point, let's start to, I mean, Rootstock is by far the biggest or the highest scale example of a merge mine blockchain. There are others. And perhaps we'll see more in the emerging Bitcoin L2 space over the next couple of years as well. But how then does it work? And feel free to use Rootstock as an example. How does merge mining work?
Yeah, I will use Rootstock as an example because there are several flavors, ways of achieving this. But basically, you have the miners of your primary blockchain. Some of them might want to merge mine. You don't need all of them merge mining. That's important. The ones that they do want to merge mine a secondary blockchain, what they need to do when they are building the block of the primary blockchain that they want to mine, they need to add an ID of the secondary blockchain block in a specific part of the primary blockchain block. And that's how it works. Very simple. One of the problems.
This is, I've heard it described before as a 0 to 1 that's different in the header of the template that gets sent out to the miners.
If we want to be more technical, you put a specific part of the block, in this case Bitcoin, a tag. And that tag basically can have any sort of information that you want. The most basic one is a reference of your block, for example, of the hash of the block header of the secondary blockchain block that you want to mine. It could have other types of data. For example, we have other types of data as well, but we can go into detail later.
So maybe then sticking on this description of merge mining, then, can you run us through some of the principles behind merge mining?
Yes. So the first one, you need to have a way of getting these IDs from the secondary blockchain. The easiest way is for the miner to run a full node of the secondary blockchain. So this has some operative costs because you need to run the nodes that consumes bandwidth and storage, but it's minimal. So it doesn't affect the proof of work computational power at all. And that's the easiest way, but you can have other ways. For example, you can delegate this to a third party. So you can just get the ID from a third party and you don't need to care about the transactions, etc. And there are other mechanisms that we'll cover later. For example, an auction process, and you just open your space and let other blockchains bid for that space. But sticking to the classical merge mining, you run a full node of the secondary blockchain, you create the block, get the ID, embed that ID in a specific part of your blockchain, in the case of Rootstock Bitcoin block, and then start finding the cryptographic solution. And it's very simple. Once you find the cryptographic solution that meets the criteria of the network, in the case Bitcoin, you broadcast that to the Bitcoin network because it's a valid solution. And at the same time, you broadcast that solution to the secondary blockchain, which is Rootstock. But since Rootstock has a slightly lower difficulty than the one of Bitcoin, it could happen that you find a potential candidate that is not good enough for Bitcoin, but it actually meets the difficulty criteria of Rootstock. So in that case, the miner is not going to broadcast that to Bitcoin, but it's going to broadcast that to Rootstock because for us it works. But in practice, merge mining, the one that I just explained, it happens in mining pool scenarios. Mining pool is a client-server architecture. You have the server, which is the pool, and then the clients are the miners. How it works is the server is constantly sending work for the miners to solve. They receive a block template and they need to find the cryptographic solution. But they are usually at lower rates than the one that Bitcoin is expecting. And why is this? Because the pool does it just for accountability purposes. It's the way the pool has to measure the amount of work its clients are doing. And later it's going to be used to pay for the miners for the work. Eventually, those miners who are trying to solve these shares are going to find a solution that solves the share, but also it's at the Bitcoin difficulty requirements. And that's the solution the pool is going to use to broadcast to Bitcoin. But we can piggyback on these lower difficulty shares. When they meet the difficulty of Rootstock, they can also be used to be broadcast to the Rootstock network because it solves our proof of work requirements. So the pool, what it does is when it finds the solution, assuming the pool is merge mining, right? It broadcasts that solution to the secondary blockchain. In our case, it would be Rootstock.
And so what then within this understanding of merge mining, what role does decore consensus play and what is it?
Okay, yeah. First, we need to define what height is because I'm going to use it. It's a very simple concept. If you depict a blockchain as a linked list of blocks, That's the simplest way of looking at it. You have the beginning and the head of this ever increasing chain. The beginning, you can put a number, it's going to be 0. The next is going to be 1. So all the natural numbers, including 0. And the last one, we can call it n. So the height is the relative position of the block you're looking at in relation to the list. The first is going to be 0. The last is going to be n. If you add another one, the last is going to be n, and the previous is going to be n minus 1. At that point, you know the number n, right? Having that defined, what happens in Bitcoin right now is you can have is less often than in Rootstock, but you can have two blocks competing to be the next best block. Basically, they are solving the same height, and it is the role of the miner decide which one to extend. In Bitcoin, what they use is the first seen rule, as I mentioned before. So honest miners, what they're going to do is going to extend, because miners create new blocks. So they're going to extend the chain and use the conflicted block that they solve first. So if there are block A and block B, if miner A solve first block A, it's going to extend that. And if later receives block B, it's going to discard it. This doesn't work for Rootstock. First of all, because we have a higher block rate, so the chances of this happening is more often, and also because we don't have a subsidy. Subsidy means, in Bitcoin, when you create a new block, you get a reward. Part of the reward is a subsidy. It's newly minted Bitcoin that you get as a miner. Rootstock doesn't have that. It only has the transaction fees. So it could happen in certain scenarios that the miner is tempted to not follow the first seen rule and mine from another block that perhaps has some more value that can be extracted. That's why we created the core, which stands for Deterministic Conflict Resolution. Is the consensus algorithm that we use is a variant of Nakamoto consensus, but tries to solve this issue. When you have competing blocks, it deterministically, the consensus algorithm, determines which is the block that the miners need to follow.
Right.
And it also has economic incentives, so that the miners that lost, because it's a competition, you have competing blocks, the miners that lost are actually going to get a share of the reward as well. So it incentivizes in that way as well.
And so when you're talking about share of rewards, there's also a fee distribution mechanism within Rootstock, which is cooperative. How does that fee distribution mechanism work?
Yeah, well, it's basically part of the same implementation. The core, our implementation of the core is called REMASC, which stands for Reward Manager Smart Contract. It's a native smart contract. It's embedded within the node. It is a reward splitting algorithm. What it does is, well, first of all, it has this selection mechanism that I explained, which is deterministic, but it also resolves how to share the reward with the miners and other actors as well. So when the miner solves a block and the block wins, they don't get the full block reward of that block. That reward is going to be sent to the REMASC contract, and the miner is going to get a share or a part of that bucket of money that the REMASC contract has. We say it's cooperative because other actors are going to get a share as well. There's also a maturity period. So the moment that you find a winning block is not the moment that you get the rewards. You need to wait over actually 4,000 RSK blocks, which is roughly 33 hours, before you actually get the rewards from your work. And it has some reasons behind it. The most important one is you have your reward stake as a miner, so you are expected to act honest because you want after 4,000 blocks get your reward, and that's the reason why it's there. Yeah.
Okay, so we've had a run of concepts around merge mining. At a high level, it's the ability for a secondary blockchain to cryptographically anchor into a primary blockchain, in this case, Bitcoin. To do that, you are sharing the proof of work mechanism with other networks and hence securing other networks from the same energy and computational resource of the primary network. And we talked about how fees are distributed and how this fee distribution mechanism is supplemental to the Bitcoin rewards that the Bitcoin miners receive. What are some of the challenges with merge mining that any merge mine blockchain would face, but we know that Rootstock faces?
Well, the first challenge that any merge mine blockchain is going to have is actually how the consensus of the secondary blockchain is created. They need to tolerate the often generation of uncles. An uncle is so when you are mining a block, the ones that do not win and were competing with you, those are your siblings. So are blocks that had the potential of being winners, but they didn't win. If you are a child, your uncles are the siblings of your parents, and it could be your father, your grandfather. So it could go in depth several times. So your consensus need to take that into consideration. Ours, Decor, does it. So we are covered in that aspect. The other challenge is for the miners, they need, if they are going to run a full node, the full node that you're providing to them mustn't introduce any additional risks because their main operation is mining Bitcoin. So whatever you do that hinders their operation is not going to be accepted by the miner. So in the case of Rootstock, it's very lightweight and it doesn't impact at all in the proof of work of the miners. The other one, which is very important, is that you need to be aligned to the main objective of the primary blockchain miner. In the case of Bitcoin, whatever you do in your secondary blockchain must not hinder the value of Bitcoin. If you are using a competing cryptocurrency as means for transaction fees, then you are competing with the Bitcoin cryptocurrency, and you won't be aligned with the primary blockchain miners, and they might just censor you.
So when merge mining was selected as a consensus mechanism for Rootstock, it was selected, the design choice involved was to make sure that there was a highly secure consensus mechanism securing Rootstock. How secure is merge mining as an approach? And maybe could you compare it to other consensus mechanisms in terms of security and give us an indication of why it's secure and maybe what some of the security challenges of other consensus mechanisms might be? Very broad question, but if you can give us a view into that, that'd be super interesting.
Yeah. Well, one of the things that are important here is also the centralization. So when you merge mine, you are using most of the time a subset of the miners that are mining the primary blockchain. So it could happen that because of X amount of factors, the subset of miners that are merge mining you is very low, and maybe you end up being merge mined by just a single pool. And in that case, you would become centralized, and basically that pool has the power of censoring you, basically controlling your chain. You, as the designer of the merge mine blockchain, are going to create it so it mitigates those risks. In terms of the security itself, we inherit the security from Bitcoin. Basically, we are asking how secure is Bitcoin mining. That's the simplest answer. In truth, you are going to take metrics such as the security budget, which is the amount of money that you pay the miners that incentivize them to stay honest, or the Nakamoto coefficient, which is the minimum number of actors that are required, different actors that are required in order to revert the chain if they act maliciously. But in practice, in Rootstock, depending on the amount of money that you're transferring, users or exchanges are going to wait between 1 to 120 blocks. Given that our block time is 30 seconds, that's roughly 30 seconds to 1 hour, depending on the amount that you're transferring. And regarding on the other consensus mechanism, if we compare it to the most popular proof of stake, they work completely different. The security of the proof of work, which is a competition, is the electricity that you're investing in the machines, and it's very energy intensive, and that protects you for certain types of attacks. And in the term of, in the case of proof of stake, what you're putting is money. You are staking money.
It's a symbolic symbolic power as opposed to, I guess, what you would call raw power, if you will.
Yeah, you need to evaluate if what you're staking has value, right? But the thing is, it's not energy intensive. But it might have other problems such as centralization of power, or also the known nothing at stake problem. Basically, the incentivization of the validators, because you don't have miners in proof of stake. Validators, which are the ones who sign and propose the new blocks. If there is a fork, which is two competing blocks, they are not in some implementations incentivized to choose one over the other. They might just validate both, because they expect in the end one of those win and they would get a reward anyway. So yeah.
So thinking about Rootstock specifically, then one of the risks to any network is a hard fork, an uncontrolled hard fork. How does Rootstock prevent forks from happening?
Okay. Yes. Well, talking about malicious forks, and with malicious we mean with
unintentional,
well, yeah, it
not
could be
something that was derived, that was performed by the community or by the community's will.
Yeah, it could be a conscious attempt or a malfunction. And what we have in Rootstock, when I mentioned what we add in the merge mining block, in the primary block, which is a tag, in Rootstock we add extra information that we use for the tool called Armadillo that we have. It's a monitoring and prevention tool. What it does, it detects malicious fork attempts, and with malicious we mean actual irrational attacks to the Rootstock, as well as faulty machines or malfunctioning nodes. And what it does, it broadcasts an alert to the network so that they can act before the fork happens. The alert system is not working right now, but it's in the roadmap, but the detection is there.
And when you think about so that's how you prevent a malicious fork of the network. Thinking about the economic principles around merge mining, what are they and how were they designed? We spoke earlier about fee distribution. I'd be interested to know some of the economic theory behind merge mining.
Yeah, well, I think it's all related, right, with security and everything. So merge mining, what it does is combine, I think, two economic principles. You have the efficiency of being able of mining more than one blockchain with the same effort or with the same cost, and also getting something in return. In case of Rootstock, we have the REMAS protocol, and the miners get an actual reward in Bitcoin from their work. But I think there's also another very important principle, might not be economic, but it's the ideological one. We are aligned with Bitcoin, and that is very important because we are expanding its functionality. So it's not just an economic incentive, it is an ideology incentive as well. And it is actually a symbiotic relationship. We are also getting something from Bitcoin, which is the security, right? So I think that's important, and also that adds to the security of Rootstock.
So we spoke earlier about the what the miners look like, these ASIC rigs. Who are the Rootstock miners? Who are the mining pools? What organizations merge mine with Rootstock today? Do you have maybe some names you could share with us?
I wouldn't get into detail with names because I might mention someone and it's not there, and maybe maybe I wouldn't have an accurate answer for the actual names that are merge mining with us, but I can say that the majority, if not all, are pools, because of the way merge mining works, and I explained before.
So the efficiency gains you get from working as a pool as opposed to working as an independent miner. Hypothetically speaking, could an independent Bitcoin miner also merge mine Rootstock?
So they could, but it probably wouldn't. They wouldn't get any benefits. They would always have a mining pool winning over them. In terms of hashing power, usually we have between 50 and 60% on average of the whole Bitcoin mining power. So it is a lot. So being a single miner, it wouldn't be very rational, to be fair.
So what are the, zooming out a little bit, we know that merge mining is the consensus mechanism of Rootstock, but what other blockchains use merge mining? Have you come across any notable examples?
Yes, I don't know about notable, maybe most of them don't have, they are not relevant, but there are examples. For example, for Bitcoin, you have Namecoin, Lanecoin, TerraCoin, Coin, which is a nice example, and I'll explain why. And for Litecoin, you have Dogecoin being the most relevant, but then you have Dingo Coin, Ethercoin, also Coin. The nice thing about Coin, even though it's not relevant, they have an approach which is a multi proof of work merge mining. Basically, they can use proof of work from different sources, in this case, Bitcoin and Litecoin. And that helps in having a more decentralized security, right? Because you have proof of work from different blockchain networks. But to be honest, the relevance today are Rootstock and Dogecoin.
A common misconception with Bitcoin is that it's this kind of completely independent, completely automated, completely static distributed computer that never needs to be updated, never has bugs. It just runs. It's this like beautiful machine. And the reality is that's not true. There are lots of Bitcoin core contributors all over the world, often being funded by grants, trying to address challenges as they emerge. And Rootstock, of course, is exactly the same. So we have contributors both at RootstockLabs, but also outside of RootstockLabs who are working to improve Rootstock every day. Thinking about the improvements that have been made to the merge mining algorithm over the years, can you maybe give us some examples of some interesting improvements that have taken place recently in specifically in merge mining, or some changes that have been explored that we're considering?
Yes. For the first one, first I need to introduce a concept which is blind merge mining. Before I mentioned that you can auction your space and delegate the block creation to another role. Well, basically, that's kind of what blind merge mining is. Basically, the miner has a spare block space in the block, and what they do is they open it for auction. Then you have a new role, which is the virtual miners, or the miners of the secondary blockchains, and they are the ones who are going to bid for that space. And when they win that space, these virtual miners are the one in charge of creating the block, and then they put the ID of their block in the primary blockchain node. The miner, the primary miner, they get the outcome of the bid, of course, and these virtual miners, they get the transaction fees. So that is blind merge mining. What we did in Rootstock is we proposed a new sidechain that is specifically to manage this bidding process of blind merge mining with an average block rate of 15 seconds, which is half of what Rootstock has at the moment. Another thing that this is important for us is what it's called inclusive fork-aware merge mining. Try to explain it without being too technical, but I mentioned that not all miners merge mine in Bitcoin. Some, they don't really care, or maybe for them, the operational cost of maintaining a full node is not attractive, so they just don't merge mine, but they are mining. So they are actually contributing to our security indirectly with these neutral blocks. These blocks, they don't have a merge mining tag, but they are built on top of our blocks. So they are adding confirmations of our security to our blocks. So this new inclusive fork-aware merge mining tries to use that confirmation hash rate the same way that today we use the uncle's creation when we try to find the cumulative difficulty or the work a block has. This has been proposed, it hasn't been implemented yet. Last one is the universal merge mining. It's very, very similar to blind merge mining, It's the same concept, but in Rootstock. Basically, it allows Rootstock to have sidechains similar to shards. And this is very important because when we achieve full capacity of our main chain, Rootstock, we can start using these shards to increase our capacity. It is implemented, but it hasn't been used because we haven't reached capacity in our main chain.
So, okay, just to kind of wrap up then, because we've been through such a wide range of different elements of merge mining. If you think about the security challenges that blockchains, including platforms like Rootstock, face when maintaining integrity and preventing attacks, can you perhaps give some examples of those challenges and maybe how Rootstock might address them and how its architecture addresses them?
Yeah, I think, for the mitigation, I think we covered them all, but I will refresh them. Basically, the things that you usually take into consideration, and I'm just going to pick a couple, are, for example, well, the most known one, which is the Goldfinger attack, usually called the 51% attack. Honestly, there is no way around the actual attack. It happens in all the proof of work blockchains. In Bitcoin, it could happen in Bitcoin as well. To be honest, no miner or mining pool has been able to maintain a sustained hashing power that is more than 51%. So in practice, it's not that realistic. It could happen. You could get there through other types of attack, but the idea is that you mitigate all the other types of attack, right? It is very
I think I'm right in saying that some of the largest mining pools today are in the high single digits, right? 8-9% of hashing power for the whole network, something like this.
Right. And it would be extremely expensive to do this sort of attack as well, especially in Bitcoin. Some other, maybe not that important, but they are attacks, for example, selfish mining, which is something that we have a mitigation for, specifically our consensus protocol, REMAS. That's when a miner starts solving blocks, but instead of broadcasting the blocks to the network, they keep it to themselves. So they start building this private chain. Why is this? The honest chain keeps growing, right? And maybe I'm going to simplify it, but maybe, I don't know, the length is 5. And you're creating your private chain, and maybe your length is 5 as well. Or maybe 6 or 7. So you're ahead of the honest chain. The honest chain is the chain that everyone who's honest is following. So you keep doing this, and at the moment that the honest chain is reaching you, what you can do is publish your private chain. The honest miners, what they're going to need to do, since your chain is larger, they're going to switch. They have to switch to your chain because it's how the consensus works. And when they do that, they are now actually trying to validate and reindex all these blocks that they didn't know. On all these blocks, you were the miner, so you are getting the reward. And in addition, now you have time while they are validating all these new blocks that were unknown to actually start creating the private chain again. So you are constantly getting all the rewards, right? In our case, we have REMAS, which disincentivize selfish mining. Another type of attack which can be used to build to other attacks, such as the Goldfinger one, is eclipse attacks. This is a focus attack. So you are trying to partition the network. You're trying to create partitions, like centralize it in a way. What you do is you have a node that you want to attack. Nodes, they connect through peer-to-peer connections, and that connection is limited, maybe to 8 nodes, for example. So the idea of the attacker is to control all those 8 nodes. 8 is an example. And when you do that, you have full control of what that attacked node sees. Basically, the whole truth of the blockchain you control. You can feed to that node wherever you want. And actually, you can censor that node, because whatever they want to send is going to be through your nodes, and you control those nodes. And you can repeat this and partition the network as much as you want. And the ways to mitigate it, is basically how you implement your peer-to-peer connection in your node. For example, peer scoring, which is something that we have. It could be authentication, you name it.
So one of the attacks is called a Goldfinger attack, and Goldfinger was, of course, a James Bond villain. If you were a James Bond villain, you had, let's say, nation-state scale resources, and you had to attack the Bitcoin blockchain, what approach would you use?
If money is not a problem, or
Money's not a problem. You've got the same. You've got sort of like top 20 nation-state GDP.
Well, if money is not a problem, given that this is a public and permissionless system, you would just
51% attack, right?
Yeah, you would just start adding miners to your pool, and that's it. It's as simple as that. If money is not a problem, you don't need to be more sophisticated than that, to be honest. If money,
it's that simple. All you got to do is take over a nation-state's sovereign wealth fund, accumulate enough wealth in the trillions of dollars to buy all the rigs, and away you go. Okay, amazing, Raul. This was deep in the details. So I really appreciate that. We have spoke about proof of work as a consensus mechanism in general, how Bitcoin mining works, what the Bitcoin miners look like, how hashing power factors into this and what it means, what merge mining is, the decore consensus mechanism that Rootstock uses, how fees in Rootstock are distributed to economically support the Bitcoin blockchain and support the merge miners. We've talked about the security aspects of Rootstock and how they factor into merge mining. And we've also talked about how Rootstock prevents forks. Finally, we as we wrapped up, we started to look at other blockchains that use merge mining, some notable examples, and some of the security and attack vectors that you would use to take down one of these proof of work networks. So it's been a deep dive on merge mining. Raul, this was amazing. I hope you enjoyed it. Raul's our Director of Architecture at RootstockLabs and one of the key long-term contributors to Rootstock. It's been amazing talking to you and getting all of this on the public record. Thanks so much. I hope you enjoyed the conversation.
Yeah, thank you very much. It's been very fun. I promise next time I will come with hard numbers to use examples, but it's been very fun. Thank you for having me.
Awesome. Thanks, Raul. Thanks, everybody, and thanks for listening in.
Thank you.